Assalamu alaikum. My name is Mumtahina Dayan Mohana. I have completed my master's and bachelor in electrical and electronic engineering from University of Dhaka. In today's lecture, I will talk about junction field effect transistor, or which is known as JFET. Let's start. So the first experimental testing of a FET device was conducted in 1955 in Bell Laboratory. Now, what is a JFET? JFET is a three-terminal device where one terminal controls the current between the other two. To explain this statement, let's look at the construction of JFET. JFET can be two types. One is N-channel, the other one is P-channel. So if we look at the construction of N-channel JFET, we can see that the substrate is made of a N-type material where P-type material is embedded on this, and the N-type forms a channel between the P-type material. It is connected with a ohmic contacts at the top and another ohmic contacts at the bottom. One of them is called drain and the other one is called the source. The P-type material is also connected with a terminal that is called the gate. And here the gate is that one terminal which controls the current between the other two. That means the voltage we applied at the gate terminal controls the current in between the drain and source, which is known as the drain current or ID. Now, if we take a closer look to the device, we can see that there are two PN junctions. One is here and the other one is here. So, under no bias condition, there will be depletion region in each junction. Now, let's have a look at the P-channel JFET. The only difference is the substrate is made of P-type material and N-type material is embedded on this. Now, the word JFET stands for junction field effect transistor. It is called field effect because an electric field is established by the charges present in the channel region. And this is a voltage control device we have seen before. It is an also unipolar device. The prefix uni stands for 1. That means the current here depends solely on the electron or the hole. Let's come to the working principle of JFET. For this, we keep the gate voltage as 0 and put the positive potential at the drain terminal. So, the drain terminal's potential is higher than the source terminal. So, electron will drift from bottom to top. Thus, the drain current ID flows from top to bottom. Now, what will happen to the depletion width when we put VDS as positive? For this, we need to explain the resistance in the channel region. Let's say the channel resistance is divided into some discrete components like this, each having a value of R. This is drain point and this is source terminal where the voltage is 0. Let's say at the drain terminal we have applied 2 volt. Now, if we calculate the voltage drop in each resistance here, we can find out this by applying simply voltage divider rule, and that will be R divided by the equivalent resistance 4R into the applied voltage 2, which results in 0.5 volt. Thus, the voltage drop here is 0.5 volt. So, at this point, the potential will be 2 minus 0.5, that is 1.5 volt. Similarly, at this point the potential will be 1 volt and at this point this is 0.5 volt. So we have applied Vg equal to 0 and at the upper point the potential is 1.5 volt. So the potential difference is 1.5. We can see that as we go down the bias is decreasing. So we can say that the upper region is more reversely biased than the lower region, and this is the reason for the depletion width to be wider near the top. Let's draw the IV characteristics of JFET. For this, we will divide the operation into 4 cases. So number 1, when VGS equal to 0 and VDS is also 0. That means we haven't applied any voltage here. Thus, the potential difference is 0 here. So, we will get no current. So, we can define this point where ID and VDS both are 0. Now, in case 2, if we keep increasing VDS, which is smaller than the pinch of voltage Vp, what will happen? Then ID increases in a linear manner following the Ohm's law. That's why this region up to Vp, we can call it ohmic region. Now, when we increase VDS, it results in two facts. Number 1 is ID increases, and number 2, depletion width also increases. Now, let's say the depletion width is increasing and making a narrower path for the current conduction. So, when the depletion region is narrowest, ID becomes saturated. It cannot increase further. So, if VDS is increased to such a point that the two depletion width or two depletion region touches each other, this situation is called pinch off. So the drain current is pinched off and becomes saturated. That is called IDSS, and that particular voltage for which pinch off occur, that is called the pinch off voltage Vp. So when VDS is equal to Vp, ID equal to IDSS, and when VDS is larger than Vp, ID cannot increase, it becomes saturated. So in this case, the device acts as a current source. Now the last and the fourth case is if we apply a negative bias at the gate voltage. So what will happen? Let's see. In the previous cases, Vg was 0. So let's say we have applied 2 volt here. So in this area, the potential difference was 2 volt. Now, if we apply Vg negative, let's say minus 1 volt, then the potential difference between the gate and the channel will be 3 volt. That means we can get the same depletion width with the lower level of VDS, and this results in the less saturation current. So from this ID-VD curve, we can see that when VGS equal to 0, ID is saturated, and this is the maximum current for a FET device, that is IDSS. When VGS is negative, minus 1 volt, ID saturated is decreased. And if we keep increasing the negative bias in gate terminal, we can see that it becomes 0 as soon as VGS reach Vp. So when VGS is equal to Vp, there will be no current since there is no potential difference between gate and channel. So the device is turned off. So this region is called cutoff region, and the Vp is called VGS off, which is a characteristic value for any FET device. Now, if we draw the transfer characteristics, that means ID versus VGS, we can see that when VGS equal to 0, we get the maximum saturation current IDSS. As VGS increased in a negative value, we get lower saturation current, and when VGS is equal to Vp, ID is 0. Now if we connect all the points here, we can get the transfer characteristics. That's all for today. Thank you.